Hello, my name is Todd Gailey. I'm talking today with Joel Klein about integrating C and Mathematica. I'll be starting off, I'm just going to be giving an overview of the whole landscape of C Mathematica integration, and then Joel will be doing the last part, talking about some of the newer technologies in more detail. I'm going to just be talking about 4 technologies in general. Good old MathLink. I'll be talking about a facility that not a lot of people recognize exists, which is the ability to call C language libraries via NetLink. I'll be talking about LibraryLink and related technologies that are new in version 8. And I'll be talking very briefly about CUDA-Link and OpenCL-Link, other technologies that are new for version 8. All right, so in the beginning, there was MathLink. And people old timers will remember that actually there was a time before MathLink. We had this thing called MathTalk, that the kernel in the front end used to, they were the same process. And if you guys remember in the early days, that version of Mathematica that Stephen launched at his opening talk, if you wanted to quit the kernel, you had to shut down your whole Mathematica session. I don't know if people remember, there's a utility called Clean Slate for Mathematica that is probably, that I wrote in 80 something, like 91, I think. It was before, and it's like the longest continuously used utility in the, people really have no reason to use it because you can just, it's very easy to shut the kernel down. But when I wrote that, there was no ability to shut and restart the kernel without killing your whole Mathematica session, so it was really important. In any case, MathLink came along and allowed us to separate the front end and kernel as separate processes. So it's just a mechanism for exchanging mathematical expressions between programs. As everyone knows, the front end and kernel communicate with MathLink, and it is at the core of a very large number of Mathematica-related technologies and capabilities. Right. One extremely important capability of MathLink is that it gave us the ability to allow users to write plugins to Mathematica, external programs that could be installed into Mathematica, written in C, and extend Mathematica's capabilities. Now, of course, Mathematica can do a ton of things and does them all very well, but it doesn't do everything. And we really want Mathematica to be an environment, a platform in which you do all of your work, you coordinate all of your work. And so it's extremely important and useful to be able to bring in these other things and just directly into your Mathematica session, integrated with all of the other graphing and recording capabilities in Mathematica. All right, so let's say you had a C function. This is this trivial add to example, which is part of Mathematica, and I've been talking about it for years. That was a signature, takes 2 integers, adds them together. So how do you call this from Mathematica? Well, first you have to write a template file, this specialized.tm file. It's very short, straightforward to write, but you do have to write a specialized file. And then you have the source code for your add2. Then you have to munge it all together, compile it all together, link in MathLink, etc. And then you get this executable program, add2.exe. And I'm not even going to run this because it's so old and boring, but you could type install, and that would launch this add2 executable program, and then you could call the function add2 just like it was built into Mathematica. It's very simple. It's important to remember that the add2 program is a separate executable. It runs as a separate process, and they communicate, the integers are sent over and back via MathLink. And of course, I'm not really talking about much in this talk, but you can, of course, you can write a C program that calls Mathematica over MathLink for computational services. This is extremely important capability. Lots of programs are doing this now, using the Mathematica kernel for computation services. I'm not really going to talk about that because there's nothing really new with this. It's well documented. It's been going on for years and years. All right. There's one extremely useful facility which I think a lot of people don't recognize, which is that a new package in A called C compiler driver. Normally it's kind of a low-level thing that you might not interact with very much directly, but it does have some really nice uses. And one thing it does is it makes it really easy to build these MathLink template programs. Now, I do MathLink development, though I don't very often write template programs. And every time I need to write a MathLink template program, oh man, how do I do this? I got to launch a Visual Studio, I got to make some project, and I got to find the files and include them, and I got to build it, and it's just, there's this activation energy required to get over the hump of actually creating a MathLink program. But the C compiler driver package makes this incredibly simple. So here, for example, this is just showing you the list of files in the this one standard examples directory. There's two files. There's an add2.c file and your add2.tm file. That's the specialized template I had to write. So I'm just going to load the compiler driver package, and I'm going to call create executable. Now, it has now built the add2.exe. If you knew the steps that this had to do, this huge stack, it knows about my compiler, it knows where it is. I have Visual Studio installed. Finds it, launches it, knows where MathLink is, knows how to build the program, and creates an exe. Anyway, if you build template programs, definitely use this function. It's vastly simpler than doing it by hand. All right, so there's something very useful that .NETLink lets you do. Not talking about calling .NET functions now. That's a separate talk. We're only talking about C here. However, .NETLink does allow you to call C language shared libraries without writing any specialized wrapper code. You know, the MathLink program, we had to write a template file. We had to compile something. You can actually call DLLs in .NETLink without any preparation. So I have to call reinstall net because I'm going to call a 32-bit DLL on my 64-bit system. All right, now, I'm going to do a trivial example. We're just going to call a function from the standard C library. And I'm pretty sure Mathematica has a way to concatenate strings, but I'm going to, in case I wasn't aware of that, I'm going to call into the standard C library to do that. I'm just going to call the stircat function directly from Mathematica. And this is the name of the DLL. This is the Microsoft Visual C runtime library. That's the standard C library on Windows. So all I have to do is I call a function in .NETLink called define DLL function. And I have to give it the signature of the function. It takes a char star, takes two char stars, and returns a char star. I have to write this one declaration. And I can use C-style syntax. You notice I just take the I take the signature of the file and I just use those strings directly. And now I can call it from Mathematica. And I've concatenated two strings. Now, maybe there's a way to do that in Mathematica. I don't know. All right, trivial example, but this is extremely handy. I do want to point out that .NETLink does run on all platforms. It does run on Linux and OS X. It's not supported there, but if you get Mono and install it, you can do this on Linux and OS X. And in case you don't believe me, this is just a session from I did last night on Linux machine. I call install net, and .NETLink knows to use Mono. It launches Mono, which is a .NET clone environment for other platforms. Here I'm calling the stirlen function. I think Mathematica knows how to do this, but in case it doesn't, this is the I'm calling a shared library file in Linux, and then I can call it. So it's extremely handy because I didn't have to write any C code or do any compilation of any kind. All right, library link. Now this is great. MathLink is great, and writing external template functions is a great thing. But there's some drawbacks. You have to write some extra code. That's a drawback. But the main drawback is that there's this MathLink overhead. And it's not insignificant. That add2 function on my machine, I can call it about 30,000 times a second. Now that's a lot of times per second. And for many, many uses, you don't really care if something takes 1/30,000th of a second of overhead just to call. But there's plenty of uses for which it does. If you have 100 million points and you want to call some function on them, then it's really going to matter if it takes 1/30,000th of a second of wasted time just to go across the MathLink boundary. And so, wouldn't it be nice if there was a way to load DLLs directly into Mathematica and run them in process? And we've not had the capability for many years, but we now have it with library link. All right, so I'll just give it a trivial demo, standard demo. There's a function called library function load, which loads. This is a built-in demo. This is the name of the library. It's just built in with Mathematica. This is not. There's no magic here. Nothing's being created. I'm just loading an existing library link DLL that's shipped with Mathematica, and it adds 1 to the argument. So it takes 10 and returns 11. So let's just quickly look at. I was calling this demo I function. That's the name of this. This is the actual code for the function. You notice that all these library link functions, they have a very specialized signature. And there's functions like m argument get integer. This is how you get the first argument the integer argument, and here's how you set the return value, and then this line here is the actual computation. Now, that's like the stand-in for what your C code is really doing. All right, so one thing to remember about LibraryLink is that it doesn't give you the ability to just magically load any DLL right into Mathematica. You have to write a specialized DLL. So for the functions that you want to call from Mathematica, you have to write a wrapper just like this that uses the specialized API to get the arguments, set the arguments, et cetera, et cetera. It's straightforward and it's well documented. It's pretty similar to what the sort of thing you'd write if you were writing MathLink programs. But you can't just magically load any old DLL right into Mathematica and call it. You do have to write some wrapper code for every function. All right, well, before I go on. But the huge advantage of this is that you get native speed. It's like zero overhead. You effectively have the same capability to extend Mathematica that the kernel developers of Mathematica have. You can write functions and large arrays of data can be shared in memory. So if you have a 100 megabyte array and you want to operate it on in some C code, it doesn't have to be copied. It can be operated on directly in place. So you really have tremendous power. And in fact, Wolfram Research developers are using LibraryLink to extend Mathematica with various modules. You really have the same sort of power that Wolfram developers have. Now, running a little low on time, so I just want to point out that you can compile. This is a little outside of the talk because you're not coming in with your own C code, but you can compile Mathematica functions directly to C as the target and run them in C. So although you're not writing the C yourself, it's good to know that you can get C language speed out of this execution. So here I'm just compiling. This is the normal Mathematica function compile, but I can set the compilation target goes to C. And what happens is that it creates the LibraryLink DLL, it compiles it, and it loads it into Mathematica all in one step. And so now I can call it, and I guess that's the right answer. And here's what the function looks like in input form. You can see it's a compiled function. It's got the standard virtual machine instructions as like a fallback. But here it's got, you can see the library function is in the guts of this thing. So that's what's going to get called. Right, I'm not going to talk about, you can get parallel execution out of these things. I don't have time to talk about that. CUDA-Link and OpenCL-Link, they're not strictly C, but they're very C-like, essentially the C programming language that you can run. There's been many talks about CUDA-Link and OpenCL-Link at this conference. There's more to come, so I don't really need to talk about it. But your machine has a very fast graphics processor, probably, and these things allow you to execute C language, more or less C language code directly on your GPU. So really, I think most people who used to do MathLink template program development would probably switch over to LibraryLink. There's a lot of very good reasons to use LibraryLink functions instead of old-style MathLink template programs. So LibraryLink, highly recommended for extending Mathematica if you want to write C. And now I guess Joel is going to talk about some of these more detail about some of these version 8 technologies.
All right, so Todd covered pretty well LibraryLink and its advantages, and I wanted us to think about building systems, kind of getting away, kind of breaking your mind out of writing notebooks and building systems with Mathematica as some part of it. And when you do that, you come to Mathematica with maybe some outside code or a need to speed things up. And that's where the C language comes into it. So you have code of your own that you want to write. You've maybe written some Mathematica, and you've identified some core inner loop that really needs to be sped up, and you identified you can write that in C. You may want to connect to the operating system in some way and get some system functionality, such as memory map files or something like that. And you may have, you've got some C code. This is what you need to work with. I need to pull this in. So we're just thinking about how can I use LibraryLink. These are some things you can bring to it. And then, of course, you can be pulling in third-party code. I've got a researcher that I'm working with that has something, or I've got some open source stuff that I need to pull in. These are all things that you can be using from Mathematica using LibraryLink. And the format that you're thinking of here, you may be starting with, you may be given dynamic libraries, static libraries, some object files, or top-level source. We can work with all of these things. So I just wanted to go quickly through how would you decide which of these technologies apply to you in your situation, and some diagnostic questions I might ask you if you're coming to me saying I have this system, I'm not sure how to structure it, or it's not running fast enough. Is there anything I can change? Some diagnostic questions that I would ask you right away would be distribution. How many users are you distributing to? Is this a one-off thing I'm giving to somebody else? Or are you working in a large defense contractor and you need to distribute something to thousands of people? Are they going to need Mathematica licenses is in the back of my mind. And does your code move a lot of data between C and Mathematica? Todd already alluded to LibraryLink being able to basically pass a pointer to tensor data. So for LibraryLink, if you said any number, it doesn't matter how many users, and if they require Mathematica, then I would say LibraryLink is good. If you move lots of data, then I would say LibraryLink is good. That's the summary. For the runtime library, and Todd didn't talk about this at all, so we'll first ask the questions and I'll explain what I mean by this. For the Wolfram runtime library, if you had a large number, a potentially large number, if they did not have Mathematica licenses, who you're distributing to did not have them, or there was a problem doing that, and you're not moving lots of data between C and Mathematica, then the runtime library might be indicated. So Todd actually talked about LibraryLink, so I'm going to talk about the Wolfram runtime library. And I should actually add to that the C code generator, because the way that you use the Wolfram runtime library always starts with the C code generator. So what we're starting with is compiled functions. You start with a compiled function in Mathematica, pass it through the C code generator to get C code, and then you're linking it, the Wolfram runtime library, either dynamic or static, that provides capabilities needed to execute your compiled function. And that runtime library, those two things together, you can compile them to make a standalone entity, either a dynamic library or a standalone executable. In the documentation, we have this low-pass filter example that I'm going to go through briefly that shows this. So the setup for this demo is that you've written this. This is just a trivial implementation of a low-pass filter, a discrete low-pass filter. And you imagine here, okay, I have my more complicated, more interesting, more cutting-edge compile example. But the idea is that we want to distribute this algorithm outside of Mathematica. And this is just in the C code generator tutorial. And I'm not going to evaluate these. I'll just highlight a couple of things. So we've got that compiled function. We're exporting it. Export supports this. There's other ways to get your C code out of this. But it's going to generate a .c and a .h file. I still need to write some glue code around this, something to interface with it, because that compiled function in C is going to be a C function that needs to be called somehow. It needs to be integrated with your main, or you need to make, if you're going to ship it as a DLL, provide a DLL entry hook into it. So I have to do some work here in C, and at the core of it, on this line I am calling low pass, which was the function that started life as a Mathematica compile function. So we do things like check error codes and emit the results from it. Here we have a a loop that's taking the tensor returned by that function and just emitting it to standard output. Todd alluded to C compiler driver, and here we are building our, in this case, standalone executable, passing in the main and the function and getting an executable. There's a lot of details we can't cover in this amount of time, and this is just kind of to get your mind aware to what the possibilities are. And well, I mean, you can be starting with a compiled function in Mathematica and ending up with, you know, writing code in PHP in a WordPress plugin or something, by going into C and then, you know, back into some other language. So I just wanted to try to open your eyes to the possibilities that that LibraryLink and the runtime library, in addition to MathLink, these all kind of give you different options for expanding Mathematica and where you can apply it, where you can use it.